We will talk about non-coherent detection in Rayleigh fading channels. So we start with a very simple detection problem in a fading channel. For simplicity, let us assume a flat fading model where the channel can be represented by a single uh, discrete time complex filter tap, which we can abbreviate as H. So the input output model would be y is equal to hx plus w, where Wm is given by complex normal distribution with mean 0 and variance as sigma square. We suppose Rayleigh fading, in which H or Hm is given by complex normal distribution with mean 0 and variance 1. We normalize the variance to be equal to 1. For the time being, however, we do not specify the dependence between fading coefficients Hm at different times m, nor do we make any assumption on the prior knowledge of the receiver might have of Hm. This latter assumption is sometimes called non-coherent communications. So first we consider an uncoded binary antipodal signaling. This is also called binary phase shift keying or BPSK, in which the amplitudes of x, they vary and they fall only under two conditions of amplitudes, which is plus a and minus a, and the symbols, they are independent uh, over time. Different symbols are independent over time. Now the problem with this signaling schemes is that it fails completely even in the absence of noise. The reason behind is that since the phase of the received signal y is uniformly distributed between 0 to 2 pi, so that is why the phase of h is also uniformly distributed over 0 to 2 pi. So at any time instant, the phase of h could lie anywhere between 0 to 2 pi, regardless of whether x is plus a or x is equal to minus a. Further, the received amplitude is independent of transmitted signal. Binary antipodal signaling is binary phase modulation, and it is easy to see that phase modulation is generally similarly flawed. Thus, signal structures are required, or some special signal structures are required, in which either different magnitudes or coding between symbols is used. So we would select and look at an orthogonal signaling, which is a special type of coding between symbols. We have two options, coding or varying the magnitude. So we will look into detail of binary communication for a system of orthogonal signaling. Now considering the following simple orthogonal modulation scheme, a form of binary pulse modulation. This is also a form of binary pulse modulation. What does it do? For a pair of time samples, you transmit either xa, which is given by a vector with elements a and 0, or at a certain time you transmit x vector b, which is at time slot 0, 0 and time slot 1a. So the transmission is done at two time slots, m is equal to 0 and 1. Now So the equation that we have here would turn into a vector form of input-output relationship in which y would be a vector that would be equal to h scalar multiplied by x vector plus noise vector, which acts as two independent symbol times. So the detection would be done after receiving y at two time instants, that is by the receiver first detects y0 and then receives y1. On the basis of these two received symbol times, the receiver makes a decision. Now this is a simple hypothesis testing problem. So before that, we need to go into the detail of this structure of vector signal detection, in which y vector is equal to h scalar multiplied by x vector plus w. Now h is a scalar from a complex normal distribution with mean 0 and variance 1, and now w is a vector with complex normal distribution with mean 0 and variance sigma square into identity matrix with size of 2. So I would have element 1 on its diagonal and zeros elsewhere. Orthogonal modulation is given by two transmitted symbols, xa, which is equal to a0, and xb, which is equal to 0a. The average SNR is given by a square over 2 sigma square. So the maximum likelihood ratio or maximum likelihood rule uh, would be first interpreted when x is equal to xa and the distribution of y would be equal to complex normal distribution with mean 0 and this matrix with the first element as a square plus sigma square and sigma square as the second diagonal element. Similarly, when you transmit x is equal to xb, the received signal would have a distribution given by mean 0 and variance sigma square and sigma square plus a square. The reason behind is, if you see xa vector transmitted has a here, the noise would be added here, and the second part at the receiver side, the only noise would be added here with the mean or the variance. There would be no power of the signal at the second time slot, and this is the opposite of this. So that is why they are orthogonal in nature. So the problem is a simple hypothesis testing problem, and it is straightforward to derive the maximum likelihood rule. So maximum likelihood rule is given by log likelihood ratio delta y.